Okay, so thank you for the invitation to give a talk at this Gelfand Centennial. So actually, I knew Gelfand for quite a long time, and probably I'm supposed to tell some Gelfand stories. So it's actually, I can tell quite a few of them, but most of them are rather personal, so they should not be told in a big audience. But nevertheless, let me tell a couple of them. So it's in the fall of 1990, so I visited for a semester, for full semester at Harvard, and for a semester, and then also Gelfand came for probably for a few days, and then I was standing in a corridor, and then Raoul Bott, apparently looking for Gelfand, so just approached me and asked him, "Where is a great man?" So second story probably goes back to maybe 50 years ago. So it was one of the recollections from the Gelfand seminar. So it was probably something 1962 or 1963. And so they studied paper by Milner on vector bundles. And so there was a definition of vector bundles, so it's quite involved, especially for older people. So you have covariance, you have transition functions, you have some condition how they, and actually it's quite complicated to comprehend unless you absorb this in a kindergarten. And so at some point, Rykov, who was Gelfand Rykov, so he was leaving the room, and Gelfand said to him, Dmitry Abramovich, so name and partner Minkowski, do you remember how it was difficult to understand the definition of a complete non-vector space? And so the last story is I'm going to switch to maybe to talk. So I remember at one of these seminars, Gelfand said that he especially values something in mathematics which he could explain to Gauss. So I don't know if he said that, but I don't know if he really meant that. So preparing for my talk, I tried to, what I could explain to Gauss from my work. Probably this will be just one slide, so it's okay. So probably this is a special case of the Oppenheim conjecture, which I proved about 20 years ago. And so the statement that for every positive epsilon, it's possible to solve this. So there is a non-trivial integral solution of this inequality. So x squared plus y squared minus square root of z squared less than epsilon, and then similar for replacing square root of 2 by square root of 3. Okay, so this is just short introduction. So now I want to maybe cover briefly two topics. So one is, maybe first switching from Gauss to Minkowski, and then there was a work which was done quite several years ago with J.D. Fafre, so it's a random Minkowski theorem. And so there is some standard definition. So it's standard definition of a lattice in Rn. So this is discrete subgroup of co-compact. And so there is a standard example. So this lattice is integral lattice, N, and also simple statement that all lattices can be obtained by integral combinations from a basis. Now there is a an important class of lattices, which are unimodular lattices, and then the covolume is equal to 1. And of course, Zn is one of these lattices. Now, there's a classical question in geometry of numbers. So it's, suppose we have a set B in Rn, and so when can we find non-zero lattice points in this set? OK, so probably in this lattice should be, so assume that it's unimodular. And of course, there should be some geometric conditions on Bn. And there is a classical theorem by Minkowski, which says that if we have, suppose we have a set B in Rn, which is convex, centrally symmetric. So this, if x belongs to the set to B, then minus x also belongs to B. And assume that volume of B is greater than 2 to the n. Then the statement, if we have a set B which satisfies the conditions on the previous slide, and assume that we have a unimodular lattice, for example, assume we have a Zn, then there exists a non-zero point in the lattice which belongs to the set B. And so remark that 2 to the n is sharp. So the proof is rather simple. So we consider the set 1b over 2, so it's divide all elements from B by 2. So then the volume of this set will be greater than 1. And then we project this set on the quotient Rn by gamma. So the volume of B is greater than 1. So the volume of Rn by gamma is equal to 1. So therefore, there are at least 2 points which have the same projection. And then we take the difference and of this point, and then they should belong to this lattice gamma. So it's so very simple proof. OK, so now it's question is, so of course, we had these conditions that the B is convex and centrally symmetric. So it's now what happens if we drop these conditions. And yeah, for example, question which we're interested in. So it's given a set of large volume, what is the probability of a random lattice which doesn't intersect this set? And now it's a remark that, of course, if we have, so it's easy to construct lattices which miss sets with large volume and even with infinite volume. So therefore, we say it's not a statement about an individual lattice about a random lattice. OK, now there's a setting. So actually this question somehow occurred in this work with J. de Favre, or we studied logarithm laws for unipotent flows. So this is one of the questions in homogeneous dynamics, and somehow we came to this question. OK, so now what is a random lattice? So it's, so one can define the space of lattices. And So if we have a unimodular lattice, if we have the group SLNR, so n by n matrices with determinant 1, then we can apply element from SLNR to this lattice, and again, we'll again get a unimodular lattice. And actually, it's easy to show that SLNR acts transitively on the set of unimodular lattices. So in particular, it's possible to get any unimodular lattice by applying elements from G to the standard lattice Gn. Now, so the stabilizer of Gn, of course, is SLNZ, so and then because of that, we can actually identify this Yeah, we can identify the set of unimodular lattices of the space Xn with the quotient SLNR by SLNZ. Yeah, of course, there is a hard measure on SLNR, so it's invariant measure, and then it descends to a finite measure on Xn, so it's, so here it's written, attributed to Ziegler. Actually, probably it had been known to Hermite and Minkowski. And also it's possible so we can normalize this finite measure so that make the measure mu n, and it will becomes a probability measure. And now there's this theorem which we call the random Minkowski theorem. Let n is greater than or equal to 2, then there is a constant Cn which is actually can be explicitly computed such that for any bounded measurable set A in Rn, say we take this hard measure mu n of the lattices which do not intersect this set A, then the measure of these sets will be not greater than this constant Cn divided by the volume of A. So actually, as I said, we needed this. So we came to this theorem studying this logarithm loss for unipotent flows, and we needed this for the case when n is at least 3. And so there's a sum, it would be. Okay, so now it's there's some kind of reformulation. So we have a set of large measures, so it's at least greater than Cn. Then the probability, so that this lattice, with respect to this measure mu n, that this lattice misses this set decays like 1 over the volume of A. And there's this estimate for Cn. So it's not greater than 8, z of n minus 1 over z of n, when n is at least 3. So it's not a sharp estimate, but it's
Zero lists every set. Every set doesn't contain zero.
No. We have a set of large measures. Yeah, so it doesn't contain 0. Yeah. Yeah, no, so actually when we came to this question, so for n at least 3, so it's somehow it was not clear how to prove this, and actually we asked quite many people and so didn't get the answer. So apparently it had not been known. Okay, so now how it's something about the proof. Okay, so there was something which called Ziegler transform, a theta transform. So we have a function with, say, we have continuous function with compact support on Rn. Then we can produce a function on the space of lattices. So we take lattice lambda, unimodular, and take the sum of the values of function f at all non-zero points in lambda. And there is a Ziegler's integral formula which says that integral of f over Rn is actually equal to the integral of this function f hat over xn with respect to the measure mu n. Yeah, no, so this was a paper by Ziegler from 1948 or something like that. And so in this paper, so he had this formula, and actually he used to give some kind of more elegant proof of this Hlavka-Minkowski theorem. So which says that if we have a ball in Rn with volume centered at 0 with volume greater than 1, then there is a unimodular lattice, well, less than 1. Then there is a unimodular lattice which misses this ball. Okay, so now it's some strategy of the proof of this random Minkowski theorem. So there is so suppose we have this set in Rn, which is bounded and measurable. And actually in this Ziegler formula, so function f is not necessarily, it's enough to assume that it's integrable. So we have bounded measurable, and now we take the set of lattices in set of unimodular lattices which miss this set A, and we want to estimate the measure of this set sigma A. And now we take the function on the space of lattices, which is the cardinality of the set A intersection lambda. How many points in lambda belong to A? So this will be this Ziegler transform of the characteristic function of the set A. Huh?
You didn't include 0.
No, this is. Yeah, 0.
This should not contain.
Yeah, so it's kind of a statement. Okay, so now it's okay. So we have this function fa, and according to the Ziegler formula, we know what is L1. But somehow it's not enough, and it's actually so we're given some advice that one has to look at L2, and so this is so using Cauchy-Schwarz inequality, so just, and there is, of course, standard trig which goes back to Chebyshev. So let's, okay, so we have this function which is, so we know the, say, positive function which we know the integral. And we want to show that this function is non-zero, so it can be zero only on a very small set. Suppose the set where it's 0 say, measure at least 1/2. Then we have an estimate from below for L2 norm of this function. So it should be square of the integral divided by this measure. So you actually multiply by 2. Or if we have Mises set has measure greater than epsilon, so it should be greater than 1 plus epsilon multiplied by this square. So therefore, if we get estimate on the L2 norm of this function, which is some small constant, which is some constant which is close to 1, multiplied by the square of the integral, then we are done. And this is what, okay, so, so this involves this Chebyshev trig. Okay, so this is strategy, but somehow for quite a long time. So it was not clear how to prove this, but then at some point, so Anish Ghosh, who was a student of Dmitry Klinbok, so he referred us to a paper by Wolfgang Schmidt from maybe 60s, which could be useful, but it didn't contain the needed result, but there was a reference to a paper of C.R. Rogers, so it's a well-known mathematician in the geometry of numbers. And there was a lemma, so the theorem, a lemma in this paper by Rogers. So we have this set A. Now, this small a is the volume of this set with large A. And then we take symmetrization of, spherical symmetrization of this set A. So we consider the ball which has volume A centered at 0, and it has this volume A. So it's really spherical symmetrization. And there's this inequality which says that you would take the L2 norm of this function fa, which is, as I said, this Ziegler transform of the characteristic function of A, then it will not be greater than L2 norm of the Ziegler transform of the characteristic function of this ball BA. And for n is at least 3, so it's relatively easy to get this upper estimate for this integral when, say, A is large, so when the volume is large. volume of large A. So it's BA is okay. As I said, it's yeah, the same volume. It's okay. It's quite a remarkable formula, but then no statement, and the proof in the paper by Rogers is based on the following lemma, which is Rogers' formula. So yeah, maybe one remark that so why do we have the condition n is greater than or equal to 3? So if n is 2, then actually it's easy to show that this integral is infinite. Okay, so there is a formula which is, okay, it's a special case of the formula in this paper by Rogers. Actually, it was in 1955. So assume that let n is at least 3 and let f be non-negative barrel measurable function in L2Rn, then you would take L2 norm of the square of the L2 norm of the Ziegler transform function f, then it's equal to the square of this integral of f over Rn, so it's kind of unavoidable part, and then there is also take summation over all possible k and q of z relatively prime, and then take integral of over Rn f of kx, f of qx, multiplied by this, and then integration with respect to the Lebesgue measure. Yes, the dm. So, yeah, this. And okay, now when we take symmetrization, so it's more or less it's relatively easy to show that okay, this of course will be the same, but but this sum can only increase. So it's, and that's, so no, this sum of these integrals can only increase, and so it's, that's how we.
Bigger than 3. What happens when I go to 2?
I will tell something. No, and I said when n equals to 2, then L2 norm is infinite, so it's, you cannot have this inequality.
So when k and q are equal to 1, then this integral under the sum is the same as.
Okay, probably
This
this.
is integral of f.
No, this should be probably excluded. Yeah. Yeah. Yes. Yeah. So it's. Yes, so it's, yeah, no, so the proof of, okay, maybe very briefly about the proof of Ziegler and Rogers formula, so they share common proof ideas, so it's, actually it works in general for p norms where n is greater, in the case when n is greater than p, and so it's, we define a function on the bounded continuous functions on Rn minus 0 to the power p, and then by this formula, which is so the value of this function on the function h, so it will be, so we take all v1 vp in lambda minus 0, and then take h v1 vp, and then integrate over xn. Yeah, no, so now it's easy to show that this function SLN are invariant, and So therefore, it's supported on, it arises from integration of the SLNR invariant measures, and this SLNR invariant measures supported in SLNR orbits of on Rn minus 0 to the power p. Now, if n is 1, then there is only one orbit in Rn minus 0, and this implies the Ziegler formula. If p is 2, there is a one orbit, somehow kind of the main orbit, the orbit of the highest, the main orbit, and this, when there are pair of vectors which are linearly independent, and so they contribute this square of the integral. And now a linear independent vector contribute this sum of a k and q and z, where k, q is 1. And now we have this. So there should be different vectors. Okay, now there is a Soroja formula. Now it's some rather simple facts how to compute, give estimates for the L2 norm of the Ziegler transform characteristic function BA. And so then we get, so this zeta function, so it's, and so this is a rather simple part of the proof, so it's and quite standard. Now, just to complete in this part of the talk, so it's, I want to point out to, about the case n equals 2. So it's, for n equals 2, this proof doesn't work, and when Afrey and myself, so we talked to Akshay Venkatesh, so he advised us to consider some, not over all integral vectors, but over primitive vectors. So it's actually this is usually called theta transform. And then there was a, there was a chapter in the book by Lenk on SL2R where gives some necessary tool to prove an estimate, to prove some equalities. And this is actually a special case of general argument which is due to Langlands and which is contained in lectures by Harishchandra. But this, the proof for n is at least 3, so it's in some sense elementary. So it's, but for n equals 2, it uses Eisenstein series and so on. So it's not, not in any sense elementary proof. And actually for n is equal to, we don't know the proof of the random Minkowski theorem for n, proof of the random Minkowski theorem. Now there is one corollary from this this statement, the random Minkowski theorem, say for n for n equals 2. So we take the subset of the set of positive number which has infinite Lebesgue measure. And now we take a random flat two-dimensional torus and take the spectrum of the Laplacian. And the statement that the intersection of this spectrum for this random flat two-dimensional torus is not empty. So this is Okay, it follows from the previous statement. So because the set of the Laplacian of the two-dimensional flat torus, so it's a flat-dimensional two-dimensional flat torus, a quotient R2 by lambda, and the spectrum is the value of the x squared plus y squared, so the square of the standard norm, on the dual lattice to this. And then it's, if we consider rotation invariant sets from, then it implies this statement. Yes, on random flat two dimension. Yes. Yeah, volume one.
This means it happens with probability 1.
What?
Probability.
Yeah, so it said that it's, yeah, so that spectrum hits the set of infinite Lebesgue measure with probability 1. So again, so it's because for n equals 2, the proof involves, say, Eisenstein series, so this is also involves this, and I don't know if it had been known, but yeah, so it's somehow it's in concordance with Y law, but doesn't follow from the Y law. So now it's possible to give the n-dimensional reformulation of this, n-dimensional version of this theorem, but one has to, this corollary, but one has to replace this Lebesgue measure by we have to multiply Lebesgue measure by certain density, which can be explicitly written. Now it's, so now there's an ongoing project with Joseph Afrey, Yair Minsky, and myself, where we try to generalize this to more general situations, so have a version of, so we have flat torus, and then, so what happens if we consider instead of the flat torus form, replace random flat torus by a random hyperbolic surface of Gen G greater than 1 and curvature minus 1. So it's, and there's a conjecture which is probably true because by induction, so it's, but so the similar statement is true if M is a random hyperbolic surface of genus J at least 2 and curvature negative 1. Yeah, so how I don't.
Would it follow from some of these calculus dynamics conjectures?
No, it doesn't follow. No, for a flat torus, it doesn't follow from dynamics. So it gives some. No, so roughly speaking, it's the statement that, so what's the correlation of eigenvalues which are far apart? So we have, suppose, two eigenvalues, lambda I and lambda j, as a function on this Teichmuller space. And what's the correlation between lambda I and lambda j? So yeah, I don't know if it's a difficult question, a simple question, but somehow at the moment it's not clear how to prove this. And now kind of the related but rather they conjecture. So it's suppose we have again a set of infinitely back measure, and we have a compact surface and some sufficiently large and generic family of Riemannian metrics on, on M, yeah, Riemannian metrics on M. Then this family should be maybe finite dimensional with some measure, natural measure. Then the statement then for a random metric from this omega, the intersection of this set F with the spectra of Laplace-Beltrami operator on MDS is not empty. Yeah, I don't know. It's maybe there's some technique in partial differential equations which can give some approach to that, but maybe hit kernel and so on. But I don't know. Yeah, for example, previous conjecture, so we have this hyperbolic matrix, but we can also consider, say, we fix matrix curvature -1 and then take the family, some family of conformally equivalent metrics and see what happens. Yeah, no, so it's kind of a new question and new types of questions. Okay, so now it's in the remaining 15 or 17 minutes, so it's I want to maybe very fast to describe some ingredients in the proof of quantitative Oppenheim conjecture, and this involves again some geometry of numbers, so it will be okay. So now it will be some similar things in the previous set of slides. So we have this notation will be slightly different. Instead of xn will be omega n. So then the space of unimodular lattices with discriminant 1 is can be identified by ln r by ln z, and then it's for every function, integral function psi on Rn, we can define a function psi twiddle on the space of lattices, and is according to this theorem of Ziegler, which was mentioned before, so we have this equality that okay, so now so in the standard geometry of numbers, so if we have a lattice in Rn, then usually people consider so-called successive minima. So we take the vector with the smallest norm, then take vectors which is not proportional to this vector with smallest norm, take again vector with smallest norm, and so on. And so it turned out that for these applications in homogeneous dynamics, so it's maybe more natural to consider so other set of characteristics. Again, it's probably rather classical, but used less often. Okay, so now there's a definition. So we have a lattice L in Rn. No, we take subspace L in Rn, and we call this subspace delta rational if L intersection delta is a lattice in L. So if in the case when delta is Zn, so it's the same as saying that L is actually subspace given by defined by linear equations with rational coefficients. Now, for every such delta rational subspace, we define D of L, which will be the volume of L by L intersection delta. And so this D of L actually is equal to the norm of the exterior product of vectors from the basis of this lattice L intersection delta in L. Now there's, by definition, the D of L is 1 if L is 0. Now if lattice is unimodular, then D delta of Rn is 1. And now there's alpha I of delta will be the maximum supremum of 1 over D of L, where L is a delta rational subspace of dimension I. And I is between 0 and n. And now one take alpha of delta, which is maximum of alpha I of delta, when, okay, I is again between 0 and 1. And somehow this function alpha is quite useful because of this estimate. So we have a bounded function f on Rn, and then again take this Ziegler transform that bounded function of complex support, then the value of this f twiddle on this delta will not be greater than C of f multiplied by alpha of delta. So this is, okay, it's called the Lipschitz principle. Okay, it's probably, it's certainly is contained in some paper by Davenport, but what is? CF. CF, there's some constant which depends on f. Okay, so now so will be some couple of technical. Okay, there's something which is one example of the use of this. So it's okay. So there's some very specific case. So we take P is okay. It's greater than or equal to Q, and Q is at least 1, and then N will be P plus Q. We consider, so N is at least 3, and now there's this particular form Q0, which is some quadratic form, which is defined by this formula. So 2v1 the n plus sum of the I squared from 2 to P minus sum of the I squared for P plus 1 to n minus 1. Now there's we consider one parameter subgroup which belongs to we can consider the orthogonal form of this form, and it contains one parameter subgroup which is AT. So multiply first vector by e to minus t of the last vector by e to the t, and keep fixed other vectors from the basis. And so then we get in one parameter subgroup in H, which is special orthogonal group of this form Q0. Now we take a maximal complex subgroup in H, which will be intersection of H with standard orthogonal group. And now there's some identity. So we take sky measure, so which is more or less forward from the definition of this Ziegler transform. So so this identity is useful. So the left-hand side actually has some kind of number theoretic meaning, and the right-hand side can be treated using homogeneous dynamics. now, so there was, so it appeared in the paper by Eskin, Moses, and myself, and applying to the quantitative Oppenheim conjecture some estimate of number of integral solutions of quadratic inequalities. And this is the following. So it's so the statement A, so if P is at least 3 and Q is at least 1 and S is between 0 and 2, or if P is 2 and Q is at least 1 and S is between 0 and 1, then for any lattice delta in Rn, so we have that supremum over all positive T, and then we take alpha of AT k delta of S, integrate, so average this over K. So we have this function alpha, so on the space of lattices is unbounded. Now we take this lattice delta, so it's a point in the space of lattices. Then we take translations orbit of this point by K, and then expand by AT. So it's a kind of a big sphere in SLNR by SLNZ. It's a sphere in which belongs to this group H. And then stated an average, so it will be, we have this statement. Now there's also some statements for when P is 2, Q is 2, and P is 2, Q is 1. And actually it's somehow, so there were 2 papers with Eskin and Moses, so it's in one, we proved this quantitative Oppenheim conjecture for all irrational forms of signatures which are different from 2, 2 and 2, 1. And this is actually corresponds to this first case. So we actually had this estimate for some S which is greater than 1. And we have this estimate in this case. Now, if we have this exceptional signatures when we don't have this estimate, and actually that's the reason why we don't have asymptotics in this case. Okay, so the main idea of the proof is, okay, so we have this function. So we have to take integral of this function alpha to the power S over some set. Function alpha is the maximum of certain functions which come from the determinant. So, but unfortunately, integral of the maximum is not equal to maximum of the integrals. And somehow to overcome these difficulties, so there's a main idea of the proof is to, okay, so first we define this operator on the space of functions on actually on this space of lattices. So we we average function f over with respect to the Haar measure on K, f of ATKX. So this average of this big sphere. And the main idea of the proof is to show that alpha I of S satisfies certain system of integral inequalities. And this is one can show that, so there is so in the case where this P is at least 3, S is at least 2, that for every positive C, it's possible to find some T that this is alpha T applied to alpha I of S, then there will be a linear term C over 2 plus alpha I of S. And there's a plus some maybe large constant omega square plus maximum of this square root. So we take alpha I plus g to the power s, alpha I minus g to the power s. And so we have this. Now there's some similar inequalities for these exceptional cases, but I don't want to do that. Now so we take the sum of these inequalities, so then, okay, we have this linear term, so it will be C over 2, but there is a nonlinear term, and there is a maybe large constant which somehow increase this constant C over 2. And there is a trick which is quite so which is the following. So we consider some non-trivial, so there is a linear combination of, so there is this function, so we take function f L epsilon of s. So we take this alpha I of s, and then take not just usual linear combination, but not usual sum, but linear combination with the coefficients epsilon of q to the I. And q of I will be this function I n minus I. And actually, as this function I n minus I will be concave, and this somehow is important in this application. So it's if we take, so there's this computation which might be not so easy to comprehend in 1 minute, but at the end, so what happens that if we apply operator AT to this f epsilon s, then there's a sum not greater than some constant plus this again, this linear term, C over 2 of epsilon s, and then there's again n f epsilon s, but multiplied by omega squared, but then there's this n which is fixed, but there's an epsilon which can make arbitrarily small. And because of that, we will have this inequality that if we apply ATSC to f epsilon s, then it's not greater than C f epsilon s plus b. And what we needed that C is not greater than 1. And so after that is one can uses something like some kind of analog of mean value theorem for harmonic functions, but it involves inequalities, but it's so it's rather standard, but again, it requires some work. Now there is some lemmas which involve in this to get this inequalities. One lemma is actually computation from linear algebra, and another is follows from Adamar inequality. We have two delta rational subspaces L and M. Then if we take G of L, so this is covolume, G of L multiplied by G of M, then it will be greater than or equal to the product of covolumes to G of L intersection M, G of L plus M. So this follows from the standard Adamar inequality. And this is actually this kind of part of the geometry of numbers. So it's probably my time is exactly over. No, this was, yes. No, inequality was square. No, there exists a solution. And this is for dimension, quadratic form of dimension 3 in free variables. No, and this is estimate asymptotic for a number of solutions. So no, they are not. No, this inequality is some kind of technical tool. Yeah.
About 6.
No, here the dimension. Okay, it's actually at least 4. So it's okay. So the exceptional signatures were 2, 1 and 2, 2. So it's actually in dimension 4 there is a free 1. The statement is true, and for 2, 2 in general is not true.
Yes.
So we can take lattice in the plane, for example.
Yes.
Unimodular lattice in the plane. And take a small neighborhood of this lattice in the space of unimodular lattice, like small ball around.
Yes.
And look at the spectra of Laplacians for lattices lying in this ball.
No. Vectors.
So you take some lattice, you take a small ball around this lattice in the space of lattice, so
Yes.
all the nearby lattice. And take the spectra, Laplacian spectra.
The Laplacian spectra is a positive number.
Yes, so each lattice gives you a certain spectrum, which is a
Yes.
positive number. So you take union of all those sets.
Yes.
Is it going to be the complement? Is the complement bounded? I mean, it's related to what you talked about. Because it's
So what? Yeah, so we take, essentially we take values of x squared plus y squared on quite many lines. No, conjecture is, conjecture for a specific, for a specific random line. But here he considers union of all.
Right. So what you said implies that this complement has finite measure, but is a stronger statement.
Probably it should not be very difficult because you take, you take this lattice, so take dual lattice and take neighborhood, and they take value of x squared plus y squared on, and probably you can obtain sufficiently large positive numbers.
And then the question is that maybe then there is a stronger statement. What if I take not a ball in the space of lattices, but some lower dimensional object? Like space of lattices is 3-dimensional, but I take something 2-dimensional or even 1-dimensional, like a curve. Will it still be true?
So your question. Probably genetically it should be true.
So maybe
genetic. If these manifolds will be sufficiently generic, then it's So basically, a question. So you have you apply this some family of linear transformations to a point in Rn, and then somehow it should not be go along sphere. So it's probably. It's an interesting question. So probably it should be. Okay, I don't. The rotation is not true. So genetically it should be true. For example, if you multiply, it will not be unimodular lattice, but if you multiply lattices by constant, by take dilation, then of course you can.
The real question is that you prove that somehow the statement is probability one. So it means points which are bad for you have measure zero.
Yes.
But is there a stronger statement? Dimension of bad points is small somehow, or
maybe it's it could be a question about the Hausdorff dimension. So
you prove that the dimension is really small, not just what dimension one.
Yeah, no, it's a question about okay, what was the Hausdorff dimension for this set of, no, but if we have a set of, yeah, but then the question is, yeah, no, actually, if you have a rather nice set, which is, so actually we had this hyperboloid in some small neighborhood of this. And for this particular case, for example, it's what can one say about the set of exceptions? You know. Yeah, for example, the first question, is it true that the Hausdorff dimension is less than maximum? I don't know. Yeah, so actually we could not prove for example, I think we had some in the neighborhood of a hyperboloid in three-dimensional space. And we could not prove it. And actually it was not clear that the statement is true.
Well, if there are no further questions, so we'll adjourn and come back. What do you think? Officially, we're supposed to come back at 10:50, so maybe
10:55.
10:55.